Okay, now we're going to get more complicated. Now we're going to start talking about mass calculations. We're going to be pulling molar masses, and we're going to be balancing the equations, all sorts of things. We're going to use all the skills at once. Big key thing, remember you balance your equation. Anything that you're going to be using the mass for, you need to go to the periodic table and pull its molar mass. And you need to make sure that you've got the mole ratio set up correctly. But most of this is handled by proper use of dimensional analysis, by really thinking about what the units are and how to set them up to cancel out. Let's look at our first example. In our first example, we're going back to propane. We have C3H8, 5 moles of oxygen, 3 moles of carbon dioxide, 4 moles of water. This is now a balanced equation. There's 8 hydrogens, 4 times 2 is 8. All of the elements have been balanced. And this one's completely worked out for us, so we don't have to go to the periodic table right now. But let's just see how it was set up. If you have 96 grams of propane, what mass of oxygen is required? What mass now? So we're looking for grams. We're no longer looking for moles. And we're given 96.1 grams of propane. This is very important because grams are not directly going to go to grams. We're going to have to change our grams into moles. In order to do that, we'll go to the periodic table. The periodic table tells us that the 3 carbons plus the 8 hydrogens, so that's the mass of carbon, that's the mass of hydrogen, is a total molar mass of 44. Why are grams on the bottom versus the top? Because the given was in grams. So that molar mass in grams needs to be on the bottom, and I'm converting it to moles. Now that I'm in moles, now I can use the 1:5 ratio to go from one compound, C3H8, to the other compound, O2. And that 1:5 ratio is directly from this balanced equation. Now, if it had asked for moles, we could have stopped right here, but it actually asked for mass, so I did one more step, and I said, okay, well, 1 mole of oxygen is 32 grams on the periodic table. That's 2 times the mass of oxygen. And I was able to calculate that the total mass of oxygen needed is 349 grams of oxygen. So again, grams to moles to moles of the new compound, moles to mass of the new compound. And then we get only grams of oxygen because every unit along the way is being canceled. So the moles canceling the moles of oxygen canceling moles of oxygen, and only grams of oxygen is not being canceled. Here's a similar problem that's all worked out. You can come back and kind of check it over, but you can see the same situation. We have grams. This is 23.95 grams being changed into moles, mole ratio from a balanced equation, and then back into grams to calculate a mass of carbon dioxide. Feel free to pause the video to analyze this one more. We're going to move on to the concepts of limiting an excess reactant. It's very rare to have exact amounts of your reactants. Usually, one of the reactants is going to be all used up. And without a reactant, the reaction will stop. And we say that the reactant that's all used up is limiting the reaction, while the other reactant or reactants that aren't being used up are in excess. There is some remaining. And the easiest way to do this is to go through some stoichiometric calculations and see possible scenarios and how to analyze the answers to tell you who is limiting the reaction, who is in excess. So let's look at this example on the next page. We have 25,000 grams of nitrogen and 5,000 grams of hydrogen, and they're reacting together to make ammonia, NH3. And we're supposed to calculate how much ammonia they could produce. Well, I've got this one all worked out so you can see what the excess and what the limiting are, but initially you can't tell. You can't tell if you're going to run out of the 25,000 or the 5,000. You actually have to do the math. first you always need to balance the equation. So I have a coefficient of 3 here and a coefficient of 2 there to balance this equation. And then I went through the steps of stoichiometry. I said, okay, grams of nitrogen, that needs to be grams because they can be changed into moles. Moles of nitrogen, that needs to be moles of nitrogen, so it could be changed into moles of ammonia. And moles of ammonia could be changed into grams of ammonia. Where did I get the 17.04 and the 28.02? Well, anytime we have 1 mole, that's represented by the molar mass on the periodic table. So this is the mass of N2 on the periodic table. And this 17.04 is the 14 grams of nitrogen and the 3 hydrogens that are in that molecule. So that's the molar mass of NH3, ammonia. Then I went about just doing the math. 25,000 times 1 times 2 times 17 divided by 28 divided by 1 divided by 1. Got this really big answer, 30,000 grams of ammonia. I have to go back through and do the same thing with the hydrogen. It's really like 2 problems in one. 5,000 grams of hydrogen. Change the mass using the periodic table into moles. Change the moles of hydrogen into moles of ammonia. Again, pulling the coefficients, 3 to 2, so 3 to 2. And then moles of ammonia changed into grams of ammonia. And what is nice is you already know this mass because you worked it out in the first half of this problem. And you get a second possible answer. Notice this answer, 28,000, is smaller than the other answer. When you get to 28,000 grams of ammonia, all of the hydrogen is gone because it's completely changing over into ammonia. And if you get to 28,000 and that hydrogen's gone, this reaction would stop. And if it stops at 28, you're not going to get up to 30, which means not all of the nitrogen, the 25,000 grams of nitrogen, are going to completely be gone. So there'd be a little bit of nitrogen left over mixed in with that 28,000 grams of ammonia. This tells me that 28,118 grams of ammonia, that's the theoretical answer. That's the answer we would expect to get. The hydrogen limits the reaction, so we call that the limiting reactant, and the nitrogen is in excess. Here we have the same concept, new problem, ammonia, copper oxide, producing how much nitrogen? So we change the mass into moles, moles into moles, moles into grams. I get an answer. Mass into moles, moles into moles, moles into grams. I get a second answer. This answer again happens to be smaller, so this would be the theoretical answer, the theoretical yield. This is what we would expect, 10.61. It comes from the copper oxide, so copper oxide is limiting the reaction, and ammonia is going to be in excess. These problems aren't much harder than the other problems. It's really just 2 questions in one. And keep that in mind for grading purposes. Since it's 2 questions in one, it's worth twice as much as one of the other questions.